My name is Madhu Mohan, and here my colleague is Nirmoy. So we work for SUSE in the development team, which is mainly focused on the networking areas. So we focus on a range of technologies, starting from the basic Linux networking stack up until the upper layers like the SDN, NFV, and the way it integrates with the rest of the ecosystem. So today's presentation is basically about how we are trying to realize NFVI within SUSE and how we are trying to address that market. And yeah, to start with that, let's say we think about technologies like which enable cars, for example, when you're driving on a busy road and you don't want to see in it, you don't see traffic lights, but the traffic is perfectly managed. And instead of the driver seeing the traffic light and traffic signal and moving ahead, the car gets a signal from somewhere and it knows what it needs to do. So in real time, every car on the road has the required signal, and it basically the traffic is self-managed. So I mean, that's probably a little bit of a science fiction kind of a scenario, but that's still possible. Maybe a little, if we scale it down a little bit, we can imagine something like virtual reality games, and maybe some use cases like live high definition video conferencing. So these are applications that we are thinking about when we want to talk about the new buzzword or the new technology we call 5G. So with that note, let's start. And what we're trying to address in this presentation is a brief introduction about what the current telco infrastructure looks like, and what it's going to look like when the 5G comes around, and how network functions virtualization is an enabler for realizing technologies related to 5G, and a little bit about what open source solutions we have, an introduction to what OPNFV is and how SUSE is being involved in that, and what are the requirements that we need to take care about to enable the technologies that we need for enabling 5G, and a little deeper into the performance aspects, and a small demo that we try to put together to show how things come along. Okay, so when we think of applications on 5G, one of the key requirement is blazing speed communication. So you want to have the devices and machines which are part of the massive IoT scale to be able to communicate in real time, and to be able to compute and provide services in real time. So for that, blazing speed communication comes with the right kind of infrastructure, telecom infrastructure. And when we look at today's communication infrastructure, so it's basically a mix of a lot of specialized hardware which are deployed in various places in the field as well as in the server farms, and custom software, proprietary software, and also custom built, which run on custom built server farms. So we'll talk a little bit about the functionalities that the telecom needs to implement. But here is kind of a list of functions that a telecom network infrastructure will need to realize in the infrastructure. So we'll go into the details of little basic introduction to that. So in a typical LTE network infrastructure that we have today, so you can simply classify two levels of networks. One is the evolved packet core, which is also called as the core network. This is the network which sits in the back office or the back end and does all the mobility functions. Like in simple terms, what we can say is, so this is the one which the telecom service providers connect to, and they're able to bill the customers based on the traffic, and at the same time they are also able to control the access network. The second level is basically the access network. So the access network is the one where your mobile phones connect to, and that's the one which is providing, this is the network where the actual communication at the local area happens, and these are controlled and managed by the core network services. So this is how a typical network, the telecommunication infrastructure looks like as of today. So the problem is, when we see what these entities here, the access, how the access network is implemented and how the core network is implemented. So we find hardware devices implement equipments like this. So some of them are from Fujitsu and Cisco and a few other partners, but yeah, just to give you a picture of how the hardware looks like. So what are they expected to do? So, but before that, what are the problems? One thing, again, they are expensive, difficult to maintain, and they are built to specific certain specifications. So if you want to customize a new service, if you want to add something, a new functionality, then you might have to probably, or the service provider might have to buy a new hardware or replace the existing hardware. So that's the problem that we are trying to address in making it software defined. So, but why do they still use it? One of the reasons would be, of course, the obvious reason is it's legacy, it's there, it's working, and people are connecting to it, and they don't want to disrupt it all at once. So legacy is one of the reasons. The other reasons could be they are performant. They are customized special hardware which are specific to the functions that they are supposed to do, and so they are reliable, and that's also the reason they are also highly performant because of the custom hardware they use, and they are secure. There is a physical security and as well as the custom build security. So the security also comes into picture. But this is how a probable 5G looks like. The application, so until 4G, the main purpose of the telecommunication infrastructure was to just connect, was just communication, and communication for the sake of communication through text. Then came data, and now we have media. But 5G claims to touch not just the communication industry, but also every other industry that we can think of through, it could be industrial automation, it could be automotive, and the gaming, and augmented reality in very diverse fields, and also voice. So the industries that it's trying to touch is varied, huge, and so pretty much every industry that uses any kind of technology would somewhere or the other, somehow or the other, is influenced by the telecom infrastructure. So that's why it's important, and that's why we are discussing it. So what are the enablers? So if you want to realize 5G in the full sense, so we basically require these 4 components, or these 4 enabling technologies. One is the network functions virtualization. So if you want to deploy new services on the existing infrastructure, you want to be able to reconfigure them and do it automatically and dynamically. So that will require virtualization. And so the functions that we are talking about, the services that we are trying to virtualize are completely network related, and so the network functions virtualization. And there's also multi-access edge computing. A lot of decisions happens at the user level. That is just before the devices connect. So when you want to have really fast communication and computing, and the results to be allocated to the devices that needs to make a decision, then it makes sense to really move the computation to the edge of the ecosystem rather than having it in the data center and then communicating the decision to the end. So a multi-access edge communication, edge computing is also one of the enablers. And millimeter wave transmission. So they're also thinking about improving the bandwidth. So communication can be improved by either by also increasing the bandwidth, and millimeter wave transmission enables just that. Right now we have communication in the range of Mbps, and with millimeter wave transmission, the claim is you will be able to do transfer rates at somewhere between 30 gigahertz to 300 gigahertz. So that's the capacity that we're talking about when we think about millimeter wave transmission. And next generation protocols, the TCP/IP is good, but that was mostly designed long ago for fixed and some wireless communications. But when we're talking about massive IoT devices, we may need a little more tweak into the TCP/IP, or maybe a new set of protocols. So a particular group from the ETSI is also trying to, which is also a standards organization, is trying to come up with new protocols and the tweaks to existing protocols to adapt to the next generation telecom. So, but what we are interested right now is basically the first one, which is the network functions virtualization. So what is it? It's basically enables deployment of network services and configuration in a dynamic fashion. So that's basically what the goal is. And the network service that we want to virtualize is the VNF, and the infrastructure that it supports. Such virtualization and management of the virtual infrastructure is what we call the NFVI, and that's where SUSE wants to play a major role in. So what can we virtualize? So the traditional IP functions, like the network security, DNS, intrusion detection. So these can be virtualized, but these are quite simple to virtualize, and we already have deployments doing that, and in terms of specialization, you don't we are aware of what goes into such functions. But the challenges come when we want to virtualize telco functions. So telco functions are firstly, they are highly specialized and complex, and at the same time they also have to handle heavy traffic load. So performance becomes one of the key bottlenecks in realizing this. So some of the functions here I can talk about are like the service packet gateways. So these gateways are responsible for directing traffic from the access network towards the core network. So in a massive IoT environment, you would probably have millions of devices directing the traffic, and the gateways are the ones which can become real bottlenecks when transferring traffic at that rate. And customer premise equipments. So I spoke about the multi-access edge computing, where the computing has to be done at the edge. So the edge devices are basically part of the customer premise equipments. So these could be virtualized and run in commodity hardware. So they are potential candidates for virtualization. And the whole evolved packet core functionality itself, which is already run in server forms, but they are quite specialized hardware. But if we can deliver the performance that those server forms can deliver, then, or with the flexibility that virtualization allows us, then evolved packet core is also another target for virtualization, all the functions inside that. And there are other services which basically go along with the core and the access network, like the IP multimedia service, and which actually runs in parallel to the core network, providing the IP and IP multimedia communication. And the mobility management entity, where which is basically responsible for ensuring that the devices have connectivity throughout, when especially when your device is a moving device, like a vehicular communication, or even a simple use case like a person sitting in a train. So mobility management entity is the one which basically manages the handover of core communication to the mobile device when the device is in motion. And the E node B functions, which is basically the core of the access network, which does all the essential functions of handling the signals. So could be things like demodulation or modulation, and error correction, congestion control, and these are the basic signaling functions that E node B handles. But in all these equipments, in all the functions, we see that we can imagine that the traffic and the amount of data that keeps circulating per unit time is massive, and that's the reason why they have to be highly performant. So overall, a high-level framework can look something like this, where the NFV infrastructure is used to host all the network functions, and there is a management orchestration block, which basically allows us to manage the virtual infrastructure as well as try to manage the VNFs. The VNFs themselves could be realized in single machines, or a cluster of them, or in general use case, the way it is realized is through a chain of service functions. And so such kind of functional management is done by the orchestration engines. But our focus here is basically on the NFV infrastructure. So, of course, there are efforts on the in the community to realize this NFV infrastructure, and OPNFV comes into picture in that case, where the complexity of the task in realizing the NFV infrastructure is basically bringing together multiple complex open source projects and integrating them together, making sure it works all the time, and we are able to realize the use cases that we want to run. So that is a task that OPNFV is trying to do in bringing together multiple open source projects like the OpenStack, OpenDaylight, and the SDN controllers, the open source storage, and also the data plane acceleration components. We'll talk more about data plane acceleration in the later slides. So bringing all these components together and also adding new features which are not available from the existing open source components. So that's the challenge that OPNFV is dealing with, and we are also active participants in active contributors in OPNFV, and so yeah. When you look at what OPNFV is doing in terms of NFV infrastructure, and this is basically the software defined infrastructure that most of the SUSE presentations would be showing. We have the we have the operating system and the virtualization infrastructure and tools that manage them, like the OpenStack Cloud or the Kubernetes, and possible interfaces to the orchestration management and orchestration layer through Kubernetes or Heat. So we have all the components, and it's put together in some fashion, in an orderly fashion. And so with this, we are also trying to realize what OPNFV is proposing as the infrastructure architecture. Now, so some of the key projects that we are currently focusing on the functional tests, basically creating scenarios. It's quite difficult to obtain real traffic scenarios for testing the infrastructure. So this is where functional test comes into picture, where it defines the scenarios for us, and it defines what kind of infrastructure is needed, and it automates the way we deploy it on the integrated system. So functional test, and yardstick basically measures several metrics to ensure that the infrastructure is compliant to what a typical NFV deployment would require. Data plane acceleration states requirements in terms of what are the metrics we want to define in terms of data plane acceleration, and service function chaining. Of course, the way we have to connect the virtual functions together to realize the required use case. There are a few other services that would be required, like the fault management and maybe policy control. These are the additional features which the existing integration may not support, and we would want to provide. And OPNFV has an extensive CI mechanism, CI project, which is done in their test lab, and we are also part of that and trying to help there. So coming to the NFVI requirements, so these are the 6 things which probably which would be needed in order to realize an NFV infrastructure. So you need to have some way to virtualize your compute resources. You need to have virtualized resources, something to manage them together, and they should be scalable. They should have a high availability, and they should be secure. And they should also have simplified service delivery. You want to add a new service to the given ecosystem, then you should be able to do it without much hassle. And they should provide reliable, high performance. So how do we meet that? One of the tools that we are talking about is OpenStack, of course. It is designed to scale horizontally, and it's fully open source. Then it's not just the open source, but it also allows us to integrate with third-party mechanisms, third-party or proprietary solutions. So one of the key problems in realizing NFVI is that you cannot really disrupt the existing infrastructure. And you need to have a way, since existing infrastructure uses legacy hardware or components, you need to have a way to integrate with existing proprietary solutions. So that's where having well-defined APIs and interfaces to integrate with other solutions becomes an important point. And some of the NFVI features which the OPNFV defined are already part of the implementation in they're already released and available with the OpenStack project, since some of the members of OPNFV are also contributors in projects like Nova, Neutron, and Keystone. And OpenStack is in production environments in several cases, so we know the problems and we know the solutions to them, and it's also continuously tested in OPNFV labs for the use cases that we want to address for the NFV market. So, do we cover all the requirements that we stated? As virtualized resources, it uses KVM. OpenStack manages them. So it is designed for scalability, and it's in production in many cases, in many places. And so high availability is also possible, and at the same time with SLES LifePatching, we are also able to have good we are also able to get the security requirements in, and service delivery is possible through several AAS projects or as a service components which can easily integrate into the existing system, and it also provides containers as a mechanism through OpenStack Magnum. And it's possible to tune your compute nodes and for real time tune for performance, and at the same time you run them on real time compute nodes. So the demo that we are talking about later is trying to use a real time kernel, and we can see what it can how it helps in realizing our requirements. And yeah, so Nirmoy will continue on few other aspects like the Kubernetes and the details about data plane acceleration.
Yep. Okay, so as Madhu was saying about OpenStack, which is mainly for orchestrating virtual machines. We have something Kubernetes, which orchestrate containers. So before going into Kubernetes, let's look into some of the terminology that we are going to use. First is container, microservice, and cloud native. So what is container? So the idea of container is to have application bundle all of its dependency into one single package, so that we can ship into any machine, any host machine, and run without any dependency issue. So we could have a host machine that using glibc libc1, and my application is compiled for libc1. And if I want to give it to my friend to test that application, and let's say his host machine is using libc2, it won't run because the runtime is different. So we have container for that. So we bundle everything into one single binary, and then let the container like Docker or LXC to run those applications. So next is microservice. Before microservice, let's look into monolith architecture of application. So in monolith, we have one application that contains all the application logic and bundle into single binary. The benefits of that is we can easily deploy because there is only one binary package and we can just deploy in a container or virtual machine. But the problem comes when, let's say, there is a bug in one of the business logic or any of the application logic, then it could bring down the whole application. Another problem is, let's say I want to update one of the business logic. Same problem happens, we need to update the whole application. The binary could also grow really big if we keep developing and adding more and more feature. And when the binary is really huge, it could reduce the startup time. So to fix this problem, we could break down those logic into microservices that we call. And each of those services take care of particular of the business logic that we have. And the benefit to get, again, let's say if you want to only update or bug fix in one of the business logic, then we can just update it and then restart that particular application or particular microservice, and the whole application works as it is. So without having a lot of downtime. So the next thing is cloud native. The idea of cloud native is to have microservices deployed as a container and maintained in an elastic infrastructure using DevOps paradigm. So these are the three components that Kubernetes has. So let's look into what Kubernetes provides. So one of the problems is service discovery with microservices. This application really need to know what are those. For here we have three, let's say, business logic. Where are they running and what are the IP addresses? So one way we can solve it, we can have DNS name. So you can assign DNS name for each of those microservices, and Kubernetes will take care of making sure that this DNS name is reaching that one-to-one microservices. And that particular microservice could run in any of the node in the cluster. So Kubernetes will make sure that it's still reachable using DNS. So that's one of the problems that Kubernetes fix using DNS service discovery. And it also has load balancing where we can run actually multiple copies of one service, and Kubernetes can load balance between multiple same services depending on the system load and other parameters. Another thing is automatic bin packing. So Kubernetes also makes sure that containers are deployed depending on the resource requirement. So we could have a container that needs more memory. We could have a container that needs particular CPU. So Kubernetes, we can configure those parameters into Kubernetes, and Kubernetes will make sure that it places those containers into particular compute node that it meets the resources. Another thing Kubernetes provides is self-healing. So let's say we have a cluster running and one of the node dies. So Kubernetes will make sure that it moves all the services that particular node was running into a particular a healthy node. So it will move all the services, or move in the sense, because if the node dies, it will just restart those services. Also, it will monitor services, and if service doesn't respond in particular timeout, then it will restart the container, or it will move the container into another working node if it doesn't respond in a particular node. So yeah, these are the three things, and there are many other advantages of Kubernetes, but I just listed down three here. So let's see how Kubernetes meets all of the NFVI requirements that Madhu laid down. So one is virtualized resources. So yes, we have a container in Kubernetes. Kubernetes itself manages those virtualized resources or container. And in terms of service delivery, it provides DNS-based service delivery. Sorry. Scalability, Kubernetes is really scale. We can add any number of nodes, and it will add more compute resources. So it's pretty easy to add and remove node into or out from Kubernetes cluster. Availability and security is similar like OpenStack. We can have LifePatching for security as well as availability, and we can also have in terms of security, is always container is less secure than virtual machine, but container is more flexible and it's lightweight. So that's a bit limited here. Reliable resources, reliable high performance, sorry. So reliable high performance is just like OpenStack that we have. We could use real-time kernel, and we can also use tuning in the Linux operating system. So let's dig a bit more deep into the performance. So I just divided into two-part, compute and networking. We could have compute or I/O, but because we are talking about NFVI, we are talking about networking then. So in terms of compute, these are the few things we could do. We could do CPU pinning. We could make sure that application use huge pages. We can make sure that application is binded to a particular NUMA socket where it's using the memory. And we could use LifePatching. It's more like a security than performance, but it's possible to have LifePatching for security enhancement as well. We could have real-time compute for less jitter, or when it's been tested that if you use real-time compute, real-time Linux, we have less latency in network packets. So CPU pinning, the idea is, let's say one of my application is running on core 0 and is waiting for a packet, and the kernel thread is running on core 1. So CPU pinning with that CPU pinning, we can make sure that the application is also running on the kernel thread that runs on particular core, so that we have this cache affinity. If they're running on different core, then CPU need to move those packets, the data around, which gives less performance. Huge page, so pages, as we know, is in memory, we divide the memory into multiple blocks, which call pages. And in Linux or even in Windows, we have pages of 4K. If we have a machine with huge memory, then the page table grows really big, and this can cause TLB misses, and again, it's bad for performance. So huge pages, with huge page, application can have, let's say, 2 megabyte of huge page or 1 gigabyte of huge page as well. So one of the applications that use huge page really well is DPDK, that I'm going to explain a bit more later on. So with that huge page, we can just assign 1 gigabyte of memory, and we never have to offload it off the TLB. So less of TLB misses there. NUMA-Affinity is something like CPU pinning, as I was explaining. So we want to make sure that process is running where the data resides. Yeah, LifePatching, we can have LifePatching for security fixes, and also LifePatching for enhancement of performance. We are going to give a bit of demo on LifePatching and as well as real time later on. The next one is a networking feature. So the idea is to have computer resource like container or virtual machine to have native performance. So in the next few slides, I'm going to explain the evolve of networking, virtualized networking that we have gone through in next few years, previous years. So in the traditional way of doing virtualized network is we use L2 switch, which is a software switch, and VMM, it could be a KMO, KVM, or any other hypervisor. So all the virtual machine connects to a software switch, and there are multiple. So when VM1 wants to talk to the outside world, so all the packets from VM1 need to be copied from VM1 memory to VMM. So there are multiple copy involved in that, and it has bad performance. But it's really simple because there are not much tuning need to be done. We can just hook a virtual machine to a Linux bridge, and it just works normally. It's simple, but it gives less performance. Next one, to fix this one, we could do something like device pass-through. So we could use the NIC and give it to the virtual machine using PCI pass-through. With that, the virtual machine 1 can directly read or write to the NIC 1, and same for virtual machine 2, it can do read-write directly to the NIC. It gives native performance, way better than this solution for sure, but the problem is we can only have few networking cards in a system. To solve this one, we have something called SRIOV. It's a single root I virtualization. With that, one NIC can appear as multiple PCI NIC devices. So the physical limit or the spec limit from PCI is, I think it's 256, but I haven't seen any NIC with 256 virtual function or virtual PCI devices. I saw with 64. So with that one, again, we could use device pass-through of the virtual function that we have. So we have one single NIC, and we can have multiple virtual function, and we can assign one of those virtual function into one of the VM, and then again VM has the ability to read or write directly to the NIC hardware. So this also gives native performance, but again, we are improving a bit from the device pass-through, because we could only have 64 virtual function per NIC, and we can only add few numbers of NIC. So again, this limits amount of virtual machine we can create for a system. To solve this, we could go real virtualized system, where in this one I'm just talking about Open vSwitch with DPDK. There are many components. We could go a bit more detail, but I'm just going to talk briefly about a few of the components. So first thing is vhost user. So vhost user is a user space device that on the VM appears as a Virtio NIC, and Open vSwitch is Open vSwitch which emulates the L2 switch, and if we add Open vSwitch with DPDK, then Open vSwitch gets the ability to read and write from the NIC directly. There is no kernel involvement, so we totally bypass the Linux kernel. And there is something called DPDK poll mode driver, DPDK PMD. So DPDK, one of the concepts DPDK has is poll mode. So DPDK operates in polling rather than interrupt, so it doesn't depend on the interrupt. So it always polls for the NIC packets. And there are different kind of poll modes for different kind of device driver. We could have Linux device driver, or we could have Intel device driver, or we could have also Mellanox, and there are different vendors. So DPDK by now support most of the vendors, and there are different poll mode drivers for different vendors. And poll mode drivers is kind of optimized. It has all those optimization, CPU optimization that we talked about. It uses huge pages. It uses NUMA-Affinity. It does CPU pinning as well. So it's really optimized for packet switching. Yeah. So this one really is one of the best, because we can add any number of virtual machine. The vhost user really scale as well as with DPDK. And we could also use for container, we could use virtual machine. So it's really flexible and it's scalable there. Well, so that's all about the evolution of networking that we have. Now we're going to talk about some of the demo. So Madhu is going to give 2 demo, and he's going to discuss some of the components that we use in the demo.
Yeah. Basically, we tried to create a sample VNF application using SUSE OpenStack Cloud. So the application is basically a video conferencing server, where the VNF that we are talking about is just doing a firewall, trying to route the traffic from the public IPs to through the network which connects to the video conferencing server. So it's a simple firewall as a service which we realize as a VNF. And for this VNF, we use the evaluation version of the FortiGate VNF component, and we are using Jitsi as the video conferencing server. And yeah. So we just configure the FortiGate so that it allows the traffic that comes and goes out of the video conferencing network. And so for simplicity, a static route is created, and the policy is just to allow the traffic that runs through the Jitsi network. And so this is basically the FortiGate UI, which allows us to configure the routing policies and firewall policies for the network we are interested in. So once the VNF is configured, so we create the corresponding infrastructure on OpenStack. So we basically have two compute nodes, and one of them is a bare metal compute node with, a physical server which basically runs a real-time kernel, and our application is basically running on that real-time compute node. So you can see the chain of network here, which is basically the traffic from the Jitsi instance is it's not so visible, that is routed through the FortiGate VNF into the public IP, so that anybody outside the network and with access control to the video conferencing server can access the instance, or the application running in the instance. I'm sorry. So we created a specific flavor for RT, and that basically uses the required tuning mechanisms that we talked about, like the CPU pinning and huge pages and NUMA-Affinity, which are the key, the main thing being the pinning of virtual CPUs. And also to make sure that this compute is, this VM is running on the real-time compute node that we have configured. So the other instances are basically not pinned. So now we have these two instances, one for the FortiGate VNF and the other one the Jitsi server instance. So let's see how the performance has been dealt with this kind of setup.
I'll stay here. Okay, so in this one, I'm going to show how LifePatching is not really affecting the application deployment. So on the right side, you can see the video streaming or the conference call that's going on. On the left side is the UI where we do the LifePatching in FortiGate. Not FortiGate, in the Jitsi server. So first thing we need to see what are the live patches available in the machine. So we use Zyper to list down all the live patches. Sorry about the font, it's too small. So we do Zyper list patches, and we give a repository. So we're going to list all the live patches that's available. So yeah, as you can see, there is one live patch is there, and it's a security patch, and we would really like to apply it. So we want to know the detail of the patch that it provides. So when you do Zyper patch info, it's going to give details. One of the details, maybe it's not so much readable, is there is a CVE, and along with other patches. So we would really like to apply it because it's a security patch that we need to fix. And on the background, the video keeps running. We haven't started the live patching yet, so let's see. So now we are going to apply the patch with again Zyper patch, and we give the first repository from where, and then we give the name of the patch. Yeah, so we ask for the confirmation. So we use kgraph for the patching. As you can see, it says kgraph patch 4.4, and there is some number. And it's being applied now, and the video streaming or the call conference is still going on without being any disruption. And we use some sort of software to actually simulate more than one client on the video server. So the patch is applied now. Let's see the status. So we use kgraph patches to list down all the patches on the system. So we have 2 patches installed. And when you do kgr status, it will say the status whether the patch is being applied or is ready. So this one, maybe you cannot read it. It says ready, so it means the patch is already applied. Patch in kernel applied as a kernel mode, kernel module. So from the ls mode, we could see there are 2 patches applied. And dmessage can give more detail as well. So you can see from the kgr logs. Okay, so that's about the live patching and how it doesn't disrupt the active running services. So the next one is we want to keep the service running, and we do CPU pinning. We make sure one of the services running on CPU 0 and is real time, and we're going to do a stress on all other cores. So again, this conference call is going on. We'll check the kernel, and it says 4.4 and RT. That's what we are interested in, is real time. And these are the GC server that is running on. We list down the CPU core. Let's list down number of threads that virtual machine is using. So you can see there are CPU 0 and CPU 1, and one of the CPU is running as a RT kernel. Not RT kernel. One of the core is running as running on RT scheduler. Yeah. So you can see they are pinned to particular cores. And with chrt check RT kernel, we can see the scheduling algorithm. So one of the core is using schedule FIFO, which is RT1. And we are going to do a stress test, and we make sure the stress tests run. Skip the score that VM is running, and we are stressing rest of the core. So we started the stress test, and you can see the conference is still going on smoothly. So we can check the process in a separate console. Let's see. So yeah, it's running the stress call, stress test. And let's see in what cores it's running. As you can see, it's running in CPU 1 and 4 to 11, so it's not touching the RT kernel core. And all the threads that it runs is also as RT. So let's see the system status. As you can see, the stress test is consuming almost 800% of CPU. We'll look into how many cores that it has, and as you can see, all the threads that it has. So it's really stressing the system, and because we have a core reserved particularly for the conference call, and it's really running smoothly without being interrupted. Yeah, that's all about the demo. Thanks. So yeah, if you have questions about all the talk, you can ask. Or if you have questions later on, you could reach to us using our email IDs. Yeah. Okay, yeah.
How is the picture with the DPDK and vhost?
Mm-hmm.
How does that work with containers? How does that look with containers? Back. Yeah, that one.
So there's a CNI plugin, at least in Kubernetes, for DPDK. So one particular is OVN from Open vSwitch. So you could use that.
So instead of Open vSwitch, OVN, there's an OVN?
It's in OVN, yeah.
Yeah.
And if you want to use not DPDK, maybe VPP, as a replacement of Open vSwitch DPDK, there is another CNI plugin for VPP as well. So you can use that CNI plugin, yeah.
It'd be nice to have a separate slide with how containers would look in this, like that.
Yeah, the presentation got really big, so I just slim it to one slide.
Have you ever compared the performance of SRIOV and the DPDK?
Come again?
The performance of SRIOV and the DPDK.
I don't have the graph yet, but we have done basic testing, and it's probably 1% less than the native one, because there is a bit of translation happens in IOMMU. So that's the only performance bottleneck there. But IOMMU is pretty performant, and it's not real native, but it's really close to native performance.
He was asking also about DPDK, not only device pass-through.
You mean the comparison of DPDK and SRIOV? Okay, I would say SRIOV gives better performance than DPDK. To reach that, you need to really optimize, do a lot of tuning. You do CPU tuning.
You gotta. In this area, with QEMU is causing the problem, not DPDK.
But if you used vhost user, there is no QEMU involved, because everything is in user space.
I understand that, but there's still probably some cache issue and CPU binding and stuff like that in here.
So once you cover that part, it gives wide rate performance. Yeah. So recently we also tested with normal QEMU interfaces, and QEMU interface also uses vhost. So the kernel side vhost, and the kernel side vhost is really doing good. I could easily reach 10 Gbps with one CPU core, so I was really surprised. So yeah, that's really nice. So we could use a normal QEMU software switch with vhost enable, and it also gives similar performance. But I'm sure with the DPDK we could scale more. I haven't done the test. I was thinking of adding more and more virtual machine and see how this setup scale with normal QEMU setup.
So you're saying in a small environment, SRIOV will do the trick, but if you need a lot of containers or VMs on a machine, then DPDK can help you.
Yeah, then you have to virtualize. More questions?
there anything special with what SUSE is doing other than this is, I mean, this is just a lot of this is just standard open source stuff. Are you just working with this, or is there anything that's special?
So we have, well, it's a communities, right? So we have maintainer and developer for DPDK as well as Open vSwitch. We have our kernel team for SRIOV and stuff like that. Yeah.
Mostly aligned with the community.
I'm sorry?
Mostly aligned with the community.
Yeah, I mean, we probably get from some requests from customer, then we kind of add those features. It could be most like a backport. So one of the problem we had was IGV device driver was not having VXLAN offload enable in one particular product. So we kind of backported to the previous kernel version. So things like that, that's what we do at SUSE. And most of the time, the upstream developer try to sync with the community and add those features along with other developers from different companies.
Well, I saw the FDIO on that. You know, with telecom, this is, you know, so you know, DPDK looks great, but the FDIO is, you know, it's got a TCP stack on user space and stuff like that. Are you thinking of doing anything with that?
FDIO, we did some research and it says it gives really good performance. We have it in our product. We don't have any requirement yet. So initial really basic benchmark says if you do really basic 2 VMs, it doesn't really matter. But if you have more and more virtual machine, then you know the graph processing of VPP is just better than Open vSwitch DPDK. But we don't have any real case test scenario yet. But we just know by reading other blogs that it's better. Yeah, if you have no questions, we'll like to end the talk. Thank you for coming.